In this example, we are going to take a look at a car collision, and specifically the car is going to hit a stationary barrier like a wall. So here's our wall, and the car is going to be here, and what we're going to look at is the amount of force applied to the car. So the mass of the car, I'm going to say, is 1,000 kilograms, and it's initially going, this is kgs, kilograms, initially going 30 meters per second. It's going to approach the wall, it's going to hit it, it's going to crumple, so the car is going to be a little bit smaller than before. It's going to be a little crumple zone here. Here's the car. And the final velocity is going to be 0 meters per second. And mass is going to be the same, assuming no parts fly off the car. So what are we trying to find here? We're going to look for the average force applied to the car during the collision, the average force. And the time of collision we're going to specify as 0.15 seconds. The time of collision is pretty short. It's a real quick pulse, or specifically an impulse. It's going to be 0.15 seconds. So before we do the quantitative part here, let's take a look at what's happening. So we know that when a collision occurs, there's a force versus time graph. So I'll draw the force versus time axis here. And that looks like a pulse. Specifically, it's called an impulse. So it kind of goes like this. It goes up, and it comes up, and it comes back down like this. And for our collision, this time of the impulse is going to be, this is the time axis, don't forget that. This is 0.15 seconds. And the important part about this is that the area of this curve is what we call the impulse. And that's the change in momentum of the car. So let's see here, the impulse is equal to the change in momentum. This is a delta, the Greek letter delta, it's like a triangle, the delta P, the change in momentum. So the momentum of the car is going from, the momentum, remember, is the product of m times v. It's going from this initial momentum over here to 0, because the velocity is 0. So we're going to change, I'm going to change momentum, and that's equal to the area of the curve. So what's the average force? Well, imagine that this were a barrier here. Put a barrier right here, and this were a piece of ice. This block of ice would melt, and it would melt and give us kind of an average value right here. I'll call this the average value, the height to which the ice melts. I call the AVG, the average value. And the area under the curved part would be the area under this rectangular part. So I'm going to take a look at the rectangular part. What this does is it makes it a little bit easier to analyze the problem, because otherwise I have an odd shaped thing here, like a little pulse, and it's kind of difficult to find the area under that thing. But if I make it a triangle, if I just say let the ice melt and find the average value, then I can basically find the area of a rectangle. The math's a lot easier. So when we get the answer, we'll get an average force. Keep in mind that that's just an average, and the peak force is a lot higher than that. But it'll give us an idea of how much force is applied to the car. So that's the basic concept. So the equation is the impulse is equal to the change momentum of the car, delta P. Delta means change in, it's a triangle, not an A. And that's also equal to the, now this is a rectangle, right? So it's the average force, AVG, times the time, base times height. So we're going to make a simplification of this pulse into a rectangle. So let's look at the variables here. P, M, and V, and then the average force, AVG, and the time of the collision. So let's see, the mass we know is at 1,000 kilograms, and this has got to be in kilograms for the units to work out. This is 30 meters per second, which roughly, if you double it, roughly, it's not quite exactly, but it's about 60 miles an hour if you double it. I don't know the momentum, but I can easily find that. And I don't know the average force, I'm trying to find that. But I do know the time of the collision is 0.15 seconds. So, how do we do this? Well, let's take a look here. the change momentum of the car is equal to the average force, AVG, that's a VG, times the time. And the momentum, the change in it is, we go from an initial value of, let's see, mv to zero momentum. So I can just put mv there, avg times time. And so the average force is equal to the mass times velocity divided by the time. So let's take a look here. That comes out to be 1,000 kilograms times 30 meters per second over 0.15 seconds, 1.5, which comes out to a value of 200,000 newtons. 200,000, if you do the math there, that's 200,000 newtons, which is a pretty big force. That would cause a huge acceleration rate or a jolt of the car, which, as you know, the collision could cause some damage. And that's, again, just the average value. So that's the value right about here. So if you look at this graph here, the peak force is actually much higher than that. It might be even double or triple that average value. So the average value gives you a ballpark figure to determine how much force the car feels during the collision. And it's just an approximation. If you were able to find the area under this curved thing here, which involves a little bit higher math, you could actually find this peak value here, the peak force. We can't do that right now, but just conceptually, that's a lot higher than that average force. So that's a sample problem of how to relate impulse and momentum in a car collision.